machine. So let's see the formal definition of Turing machine. A Turing machine is another mathematical model which is used to define the language. It's way more powerful than the PDA. It's more close to our current computer, and it is and you can see that if our machine, if you design a mathematical model and it respect these six properties, so then we can say that this is a Turing machine. What are those six properties? So Turing machine is denoted by TM. Its abbreviation is TM, and um, again it has a set of summation. Summation is used for the input letters. So anything which is part of summation, so you can use that as input letter, and lambda should not be part of the summation, so it should not be part of that. The blank symbol. So there is a tape. Excuse me. So there is a tape. So we do have a concept of tape here, the way we have in PDA. So again, this tape is something like this. Let me go to the next slide actually. So we have this tape. So this tape is the concept. Uh, so the concept of tape is like this. It has again the same thing, the cells, and each cell has ability to store only one letter, and it is infinite in nature. It starts from left to the right side, and then it will and then it can grow there on the left side, on the right side. So now if you see this tape is little bit different from what we saw last time. So far this is exactly the same, a tape finite to the left but infinite to the right, divided into cells. This is the same thing. The tape contains the input words starting in the first cell. So the tape will have these words, input words. So these words, which is mission, should store into the tape, and that will be your the way you start. It will be the input. The rest of the tape is filled with the blanks, and the blank is the delta sign. Okay, so now we are saying that we do have a index or a tape head, and this index or tape head, look at this one, is initially on the extreme left side of the first cell. And by default, when you create a Turing machine and when you start working, initially it in the Turing machine and its tape initialize this way, that the index is always on the first cell from the left side, extreme left side, and this is an index. So this will be your your index. This is called a tape head. And then you do have another set here, exactly the same way you have another set for the output characters. In the PDA, you do have the same concept here. For output characters, it will be gamma, and this will be considered as look at this for the output characters. So this will be another set. So anything in this will be your output. It can be same as your input set, it can be different from your input set. But that's the reason that we do have this notion of two different sets, because if it is same it's okay, but if it is different, so then it will be hard to manage with one set. So you have two different sets, one for the input, one for the output, and the output and input characters, its letters may be same, may be different. And again, you cannot put delta as the letter in the output set. So then we do have a Turing machine which is composed of the finite number of states, can be denoted as Q1, Q2, Q3, and it has exactly one start state. So you know that from the Turing machine from where you should start, and maybe it has no halt state, or it has one halt state, or it has more than one halt state. Some maybe none halt states. Okay, so this is your Turing machine. And then the label of the edge, how you move from one state to the next state. So normally you saw that the label will be like this. In your FA, it will be just a letter. In your TG, it is more than a letter. But now here it is composed of three things. So this will be close to the program nowadays, the way we create the program, the instructions, it is more close to that. So this will be the label of your edge. We call that a program, and it will be composed of three things: the transition, the print character, and the direction. Okay, so this will be three things. When you see example, so you can get better idea what are these things. And then the direction will help you to move the head tape head. So let me show you. So this is the final state. So no transition out of the final state. So this is a halt state, we call that as a final state. And then this is your, okay, look at this one. This is your two states, any two states, and its label is composed of three things. One is, as it mentioned here, transition, the print character, and the direction. So what input you will see and you move to this state. So might be this state has two outgoing edges. So if this is A or this is B. So this first letter is your input. What is the input? And you choose, this will help you to choose that which edge you should choose. I should choose this edge or this edge. So now the first letter will be input, the second letter will be output. So if you have this input, what should be the output you want to write here? So this output will be on the, it is decided here on the edges of the Turing machine, but its impact will be on the input tape. So exactly something like this. So you are saying, let's say if this transition is something like this, and then it says this. So now I am, what does it mean? It means that if you read A from the input tape, replace this A with capital A, and move one step right your index from the input tape. So delete this index from here and move one step right. So this is basically idea. So now in this input tape, in the PDA, you saw last time that you can move only one step towards the right side. You cannot go back. You cannot edit the tape. But now here, you can move on the right side. You can move on the left side one by one. You can delete any value here. You can edit any value here. You can delete any cell here. So you can do anything with this tape. So you can move right, you can move left, you can insert a new node in between, you can delete a node, existing node. So anything you can do that. Okay. So now so PDA will give you more control on the input tape. That's the reason that what benefit we were getting by using the combination of stack and the input tape in PDA, we are getting both benefit, both functionality only by input tape. That's the reason that we do not have the data structure stack in the Turing machine. So Turing machine does not deal with the stack. It only deals with the input tape, but the input tape is quite dynamic. You can move forward, backward, and you can edit any cell in this. Okay. So that's the idea behind that. So now the first letter is the character the tape head reads from the cell to which it is positioning. We are talking about the input tape. The second letter is what the tape head prints in the cell before it leaves the cell. And now you have only two notion of the direction. One is R, one is L. You want to move right side, it will go one step right. You want to move left side, it will go one step left. So you can traverse in between these different cells of your input tape. Okay. What mistakes you will do? You will start moving right and left in the Turing machine. So right and left. No, this right and left does not mean that you need to move in the Turing machine. It means how you move your index in the input tape. So direction relates to the input tape. Input relates to the input tape. Output relates to the input tape. All this instruction, this program, this label relates to the input tape. It has no impact on your Turing machine. Okay. So now that's the thing here. and the Turing machines are deterministic. So this is amazing. Turing machines are deterministic because this means that this machine is autonomous. It does not require human input. So there is at most one transition out of each state labeled with the same first letter. So it takes care of garbage collection. So, but also even it is deterministic, it takes care of garbage collection, machine crash. So what are the different reasons that machine crash? So one reason is this: you have input tape and your index is at the first at this point, and you give instruction to move your index to the left side. Now it cannot move left here because it is out of bound. Yes, so your machine will crash if you give this instruction, so your machine is crash. So if there is no or another thing is, regardless it is deterministic, might be sometimes you have a state and you are only taking care of A, you are not taking care of B, and you have B input here and you have no idea how you move, how you handle that input in the Turing machine, so your machine will crash. So if there is no arrow labeled with a letter in the cell pointed to by the tape head, so machine will crash. Or if it tries to move left from the first cell, this scenario or this scenario, so machine will crash. So word will be accepted when you reach at the final state. So you have this final halt state. Once you reach at the halt state, so it means that the word will be accepted. That's the idea behind that. So now let's see one practical, I think, okay. So how it executes, execution terminates successfully if a halt state is entered. So halt state may be accepted or may be rejected. It rejected means the machine crash. I already explained you machine crash because of two reasons. You have an input and the Turing machine is not handling that input, or you give the instruction when you are at the extreme left side first cell of the input tape and you ask the pointer to move more left, so it is out of bound error. There is no another first cell before the first cell, so it will crash. uh, the execution does not halt sometimes if you stuck in the infinite loop, something like this. So you are saying if you have delta, replace that with delta and move one step right. So let's say, just imagine that you have just two words A and B, and now you have all infinite delta there, exactly the way you have input tape. And you are saying read delta and replace that with delta and move one step right. So now you again it is delta, you read delta, replace delta, move one step right. So it is infinite because the size of input tape will be infinite towards the left, towards the right side. So this will be infinite loop. So it will only crash at some stage when the stack will be full, or you reach to the last, because it is an infinite memory, but still memory has some limitations. So after a few hours, it will crash. So the tape head moves to the right one cell at a time forever. Okay. So now look at this one. So we have this machine. This is our Turing machine. It has exactly one start state. It has some states. It has one halt state. Halt state maybe you do not have, or you have more than one halt state. So anything can happen. And you see the label of the edges are the instructions. AAR, BBR, BBR. So all these are the label of the instructions. So now how we start reading this, how we dry run this. So this thing is given to you, this input tape is given to you, this word is given to you, and the index of the tape head is already given, which is always be by default. When it start first time, it will be at this cell, which is the first cell from the left side. So this is given. Now you want to see that whether this word ABA will be accepted by your machine or not. So I can say that, okay, when I start from here and I read, when you are here, when you are at this place, so it will give you the read instruction. So you read from your input tape, and what you are reading A. So it means I read A. I follow this path. So what is this instruction? It says when you read A, replace that with A and move one step right. So I read A, I did not did anything, I replace that with A with the same thing, and I move one step right, and I come here at state 2. So now I am here. So when I am here, I will again perform the read operation from the input tape. And what I read B. So when I read B, I am handling it here. I'm saying when you read B, replace that with B. So I replace this with B and move one step right. And I move one step right. And when you are here, so you have A here. So when you are here, so it says now you are here at state 3. So it says when you have A, read A, write that A and move one step right. So I read this A, I write A back, and I move my pointer to one step right. And it says if you read delta, then write delta and move one step right. So I read delta, I write delta here, and I move one step right. And I'm here. Actually, there is also delta. And I am at the halt state. So once you parse this word, you reach at the halt state. It means that this is a valid word. It belongs to this machine, and it is member of this word, and it should be accepted. So you finish at the halt, you finish the word, you are at the halt state, word will be accepted. You finish the word, you are not at the halt state, you are somewhere in between any other state, your word will be rejected. And you can see this information here, what I just did, the dry run to you, that you finish at the halt state. Easy, it's not hard, huh? It's quite easy. Simply we are just doing the dry run here, we are not doing any sophisticated job. Okay. So now we will see this another example here. So this is your non-regular language, and this is a machine. It has a start state, some states, and a halt state. So now let's dry run this. Look at this one. So it has two different sets. One set is for the input letters, and one step set is for the output letters. You see, output is combination of small a and capital B. So output can be anything. Input must be small letters. Input never be big letters. But output can be anything, and then you can see that how we can deal with this. So it is basically a programming. Someone already designed this for you to for this machine, and he managed that, how what should be input, what should be output, and how he can manage that, what is the logic behind that. It's already done. Our job is at this level, at the undergrad level, we just want to do the dry run of any given word, and to see that whether it is member of this language or not. Okay, that's what we want to do. So now we have this machine, and we see that this is a non-regular language, and let's see how we dry run here. So now we are saying, I just copy paste here for you in the same machine here. So we start from here, and this is our input tape. So I mean, it should be something like this: A, 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 B, 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 and delta. Index is here initially. Okay. So we are saying start from here and read. When you are start, automatically it perform the read operation. And what I'm reading A from here. Okay. It says when you read A, replace that with capital A. So I replace this A with capital A. Okay. And then, so I start from here and I am performing this, and then move one step right. So what I should move? The index. Index should be moved to one step right. And I achieve this. Underline means you are at this input, you are at index is at that point. And now you are here at state 2, and you are saying when you are at state 2, perform the read operation. What you are reading? You are reading A here. It says if you read A, do not do anything, just replace that with the same thing, move one step right. So I did not did anything, and I move one step right. No changes in the input tape. And you have this A. So now, but it is a self loop. It means you stay here. So it says if you read another A, do not do anything, move one step right. So I read another A, I do not do anything, I move one step right. And now it says I have small b. So now if I have small b, it is this. So it says if you have small b, replace that with capital B and move one step left. So I have small b, I replace this with capital B and I move one step instead of right, my index one step left, come back from where we start, one step back. And now I am at state 3. At state 3, you are reading small a. So instead of self loop or this, I go down. Self, if you read a, do not do anything, just replace that with a and move one step left. So I read small a, I'm not doing anything, I move one step left. And then I am here, it says if you read another a, do not do anything and move one step left. Okay, I have another small a. I do not do anything. I move one step left. So now it says read. So I read and it is capital A. It says if you read capital A, do not do anything, move one step right. So I read capital A, I do not do anything and move one step right. And now I am again at the start. So what you see, we read, we change first A into capital A and we encounter capital B. For the first B, we change that into capital B. And you, this is the, so now, and you are again come back at the start state. So now the whole process will be repeated and you need to repeat this A into capital, this B into capital, then this A into capital, then this B into capital, and once everything will be capital, so then you need to see that the circuit will take you to this part where you are saying you have lambda, delta and r, and you reach to the halt state. So all these steps will be done by one by one. If you follow, just do the dry run on this machine the way I just did one iteration, exactly the same way you need to perform next 3 iterations for all 2 remaining a's and 2 remaining b's, and you reach to the halt state. Any question, guys? So Riley, are we good? Do you understand this? Okay. Quinton, are we happy?
Yep.
Nikhil, Mason, are we good?
Yep. Yep, I'm good.
Mason, I noticed that you missed the quiz or the quizzes 6 and 7. Is it you? I think
I did them at like 4 o'clock yesterday.
you did.
Yeah.
Oh, okay, then
It was
someone
at
else.
4.
Someone else. Someone missed the quiz. I don't know who, both quiz 6 and quiz 7. Um, so contact me if you want to do that. Okay. Anyways, so so yeah, we done this. This is good. It's very easy. That's the Turing machine. So you just need to dry run. So now we have this another machine, and you have this start state, and again, you the word is given to you, and you this is a word, and you need to do this. So let's try to do this here. So we have this word. And what is this word? Let me write A B B A B B A B B A B B A and delta. Oh, it's very tight, so I need to might be more big. Okay, and pointer is here initially. So you are saying I start from here and I read. What you read? You read small a. Okay. Small a means I follow this path. And what I'm saying, if you read small a, replace that with delta. So I delete. So when you replace that with delta, what does it mean? you want to delete it, because look at this one. When you have delta, so it means you are deleting. So I put delta here, so this word is gone. Look at this one. So when you have a, you replace that with delta, it is basically you are deleting this. So you are deleting this. So put that with delta and move one step right. So I move one step right. And here I have B. It says it's a self loop. It means as many time you have B here or A here, small a, replace that with the same thing, means don't do anything and move one step right. So I read this B, I move one step right, A, B, B, A, I until this one, I am not doing anything and I am moving one step right. So once I have A, I move here one step right, and then when I, and this is because of this thing and this thing. So now once I reach to the delta, so look at this one. It says if you read delta, replace that with delta and move one step left. So delta, replace that with delta means don't do anything and move one step left. I come back here. So now when you reach here, so then what you read A. So we follow this path. You read A, replace that with delta and move one step left. Replace A with delta and move one step left from here. And now it says if you have A or B, don't do anything and keep moving to the one step left. B, A, B, B, and I read here. And I keep repeating one step left. So now once I reach here, it says if you have delta, don't do anything and move one step right. So I move one step right. So now once you reach here, you come back here in the start state. So now what if you notice that what you are doing, you are basically read everything and you delete the first letter and the last letter and convert that into the delta. So this is palindrome. So palindrome means that whatever you read here, the last letter should be same. So now if you have B here, this should be B. If you have B here, this should be B. And finally you have one A. So and end of the day you end with putting everything delta. And once you have everything delta, so it means that everything is gone and your input tape is empty. It means that this is good because the way you delete, you always match the first letter with the last letter. If it is same, you put delta there. And so that's the way your machine is designed. And if it is not palindrome, your input is not palindrome, so you will have A here and let's say B here, so this machine will crash. It will not work. So that's the idea behind that. And look at this one. Finally, once you're done, then you reach at the halt state. So halt state means that everything will be delta and you are at the right and you are at the halt state. So that's the idea. You can run this palindrome and this machine and you can reach to the halt state. Exactly, look at this one. So once you have nothing, so on the input tape, so you will be at the halt state. Okay. So that's the description is written here. So now it says that for every regular language, there is a Turing machine that accepts it. So if you have a regular language, there must be a Turing machine which will accept that. So we transform an FA into a Turing machine. So the start state of FA is the start state of the Turing machine, add a halt state to the Turing machine and one transition from every final state of the FA to the new halt state, label the new transition, change each label A of its FA to AAR, and similarly for all other letters of submission. So let me convert one FA into Turing machine so then you can better understand all this discussion. So this is basically the steps how you convert your FA into Turing machine. So let me do one example so then you can understand. So it says that, look at this one. So we have this example here. So it says if you have a start state, so you must have a start state. Okay, we have a start state. Okay, and then how many states you have of FA? That much states you will have for your machine, for your Turing machine. And what should be the label? So exactly the same way, because this is start. So you need to, sorry. So you need to connect this with this machine. And you know that it means that, oh, what I did. It should be B, and you are saying it because you are not changing anything in FA, and you always move in one direction, which is right. So always our label will be exactly the same way. So you draw this and you are saying B, B, R. Okay. And then you draw this. You are saying its label will be A, R. And then you draw this. Its label will be A, R. And then you draw this B, B, R. And then you draw this B, B, R. And then you draw this. It is A, R. And then you draw this. It is again A, R. And now you notice that this one is a final state. So when it is a final state, so then you need to create a halt state with that halt state, and it should be connected with the start state, and its label will be lambda, delta, delta, and R. So this is a fixed design, and this way you convert your FA into Turing machine. So look at this one. So this is your final state. So it should be connected with the halt delta delta R. So B will be BBR, this B will be BBR, and how many states? That many states you have here, and each label is simulated with the same thing, AAR. So you always have the fix this input, and you always move right side in the FA because FA does not allow you to go back on the input tape. So FA is only one-sided direction and letter by letter. So that's why we have fix R there. Okay. So this is this is easy thing that you can convert your Turing machine into FA. And then we have this regular expression. We can convert this regular expression into FA. So it says that if you have two A's, you don't care what you have in the start, you don't care what you have after that, and then but you must have somewhere two A's, and the word will be accepted. So we are saying, okay, we are asked to draw the Turing machine for that. So we have a start state, and so let me draw this here. So we have a start state, and this start state can have anything. It can have B, B, R. It can have, and the starts, and then uh, it has delta, delta, R. It can accept lambda also because of star. And then you have A here, A, R, and this is one state. And then you have another A, R. So, and then you have a halt state, because two A's will take you to the halt state. And once you reach at the final state, we don't care what's going on. So I mean, we don't need to do this because halt will stop your process. And here you can have, if you have B here, so you don't want to crash the machine, so you are taking care of garbage collection because of FA. So BBR, if you have B here, you move back to here, and that's it, and you reach the halt state. So this is the way you convert the FA into the Turing machine, uh, because you need to create that path which is mandatory to reach to the final state. So which is 1A and second A. And then you are at the halt state. Once you are at the halt, once you reach at the halt, regardless how many letters left in your word, you do not see that, check them or parse them, because you are already at the halt state, and that's it. So then you don't need to take care about what's come after that. So because you meet the condition. So just imagine that we are saying that we will accept a word that have double A. We don't care what come before that, what come after that. And let's say you have one B, and then you have two A's, and then so much after that. But once you meet this condition 2A's, it means regardless after that it has million letters, the word will be accepted. So you don't need to take care of this part, okay? Because you meet the condition which is required to the accepted. So once you reach at halt, so you meet the condition. You don't need to check what's after that. The job is done. But here, yes, if you have one A and then you B, so you need to handle it here. So you will machine will not crash. Okay, so this is the one thing, and then this is another machine here, which is another non-regular language. It is AN, BN, AN. Uh, and again, you have a word, and the word is given to you. Let's say this is a word which is given to you. I like this way of solving. I want you in exam, in assignment, solve this way. So start, and where your index is, underline that and write the number, that which state you are, at which state you are, and then do this way. So look at this one. You start from here and you read. Read what? A. A means read A, replace that with star and move one step right. So you read A, you replace this with star and move one step right. And then it's simple dry run. So you dry run here, and finally, if you see, look at this one. And you finish here, your input table is complete star, and you reach at the halt state and you are at the delta. So the word will be valid, it will be accepted. So I mean, it is simple a dry run. So, but you just follow the instructions. So only thing is when what mistakes you will do. So this R does not mean that right left here. It means right left on the input tape. This index, okay. And this is the output which you need to write here. So this is the output which you need to write here. So and the star. So this is, look at this one. So what does it mean? Look at this one. A star R. Read A, move one step on the right side and replace this A with the star. So this is basically, if you do this, that's it. It's nothing more than that. It's a simple dry run. Okay, and you reach here. So now, as I told you that you can insert a new node into this one, and you must know, if you took the data structure course, that there is a fixed algorithm. If you want to insert any node in your array or single linked list, double linked list, there is a fixed way. If you want to insert a node in a tree, it's a fixed algorithm. So exactly any insertion or deletion is a fixed design circuit for this Turing machine. That's the reason that because it's a fixed circuit, so we do not sometimes design the circuit in our actual diagram. We just draw this insert button here, and implicitly it has a circuit there. So what we are required to do that, when you are asked to insert B here, so your pointer is here, and you have insert B, it means you want to insert B here. So it means that first you keep this anchor, some position, some information here, that from where you want to insert, and then move your index to reach that point where you have the delta. Once you reach delta, you go back to the one step behind and move this thing to this place, and then move this to this place, then move this to this place. And now if you see this is A, so move this to this place. When you move this to this place, so this place is empty. Here you insert B and the job is done. So that's the idea, that you reach to the last node, which is delta, and then go back one step and then move everything here. And then the cell will be empty. There you can perform, you insert B operation there. So this thing, how you achieve this is a fixed circuit for that. So what this circuit is doing, it is taking care of all these inputs regardless how long it will be. So first it will go here to the end and then come back one step and move this here, move this here, move this here, move this here, and then perform whatever you want to insert this thing here. And this is done by this fixed circuit here. So it's that's the reason that we call this as an insert circuit. It's a Turing machine which is taking care of insertion. If you want to delete, it is. So now look at this one. So this is a whole machine, and there you have insert operation. So once you perform insert operation, so you carry on your machine, whatever your machine is doing, you can perform that job after that. Okay. And then, so look at this one. It says all dry run, just simple dry run on the machine. And when you are talking about the delete operation, so this is also, it's more easier than insert, because in case of insert, you need to remember what you want to insert here. In case of delete, it's way easier. So you are here, so you want to delete this information. So you go to the next step and copy this into this place. So this will be empty. Copy this will be into this. This will be override. Copy this into this. This will be override. Copy this to this. This will be override. Put delta here. Put delta here. This will be override, and R will be gone, and everything will shift to one step left, and you will have this new information here. So you do not have R here, and you have I, E, and D, and you have delta here where it was previously D. So this is your delete operation. So for deletion of the any node in your input tape, it is also a fixed job, regardless whatever the input, whatever the output, how the machine, what is the language. So the process is same for the deletion. So because the process is same for the deletion for any node or any cell, if you want to delete that, so it's the same process. We have a same circuit for that. So this is a deletion circuit. So what this circuit is doing, it is overriding and moving the whatever the location you want to delete. So it goes to the next step and copy into the previous place, copy into the previous place, copy until you reach delta, and the job is done. So this is doing that, and that's the reason that we do not draw this. We just put the delete circuit there. So this is a delete circuit, and just we can represent that with a button, and that's it. So there is no creativity into this. It once it is designed for all machines. And here we done this job. And any question, guys, in this chapter? So most of the time, only two things I'm expecting from you here: how you convert your FA into Turing machine, and you should know how you dry run on this Turing machine. So if you know the dry run on this Turing machine, the job is done. So this is the only thing which you need to understand in this chapter. Questions? No questions? Okay, so let me stop this recording.